Thank you for having me here today. It's a great pleasure to participate to this great workshop. And today I'm going to talk about some of the ideas that we have been sort of developing and thinking regarding how can we build an ecosystem for research on touch sensing. And the slides are also available online. So if you're interested, you can go there and see a more high resolution version of the slides. So, and I don't see you for some reason, but well, I hope you will hear me well. So the first points I want to start from is to acknowledge the fact that touch sensing is a hard problem. It's a hard field to work on, and fundamentally one of the reasons why this is so difficult is because of the interdisciplinarity of working in touch sensing. To a large extent, there is a very vertical integration of touch sensing, from the hardware design to be able to process these images or general signals from sensors, and then integrating these sensors into robot hardware, integrate them into the control of these robots, and ultimately using it for applications. And this is really a lot. And if you think about it, it also requires a very diverse set of skills that are not always easy to sort of to capture and to have in the same place at the same time. And effectively, this has led in the past to having a lot of works which are presenting ad hoc solutions, and typically, there is very little reuse of existing components. This means that, in practice, if I want to test a new sensor, I will I will create a new sensor. I will create some new benchmark that I want to evaluate it on, and then I will, maybe create some machine learning model, but it's very difficult really to compare. And it's also very difficult to reuse this code across different sensors or across different applications. So what it means in practice is that this leads the whole field to have a very high entrance bar for new researchers and practitioners, because they need to be expert and have skills in a number of different fields. So some of the things that we have been thinking, and this is really going to be the core of the talk I'm going to give today, is our question along the lines of how can we lower the entrance bar for research in tactile sensing? How can we improve reproducibility of the science that we do? And ultimately, how we can accelerate research by trying to reuse existing components rather than every time sort of starting from scratch. And the answer to some of these questions will ultimately be that we believe very strongly that we need standardization. We will need more standardization in the future moving forward, and this will inevitably lead to the creation of an ecosystems of tools. And this is something that we've been really striving in the last couple of years, and we've been working very intensively on. And what it means in practice, if we look at the sort of at touch sensing as the goal, at the core of the problems that we want to investigate, there is in practice a very large gap between this field and this idea that touch sensing is useful and the real applications where we actually want to apply these techniques. So how can we make touch sensing practical and useful? And as something that I already presented last year at RSS, we have essentially thought, and we think that there are four fundamental pillars that are useful in order to think about the problem and to sort of guide the type of research that we are doing at the moment. And these pillars are a hardware, simulation, touch processing, benchmark, and dataset. And all of these four pillars are functional, are essentially very tightly interconnected and are functional to be able to apply touch sensing, investigate touch sensing, and have real-world applications. So starting from the first of this pillar, which is hardware, you all know that there are a plethora of really cool tactile sensors out there, and last year we tried to give a very small contribution just by open sourcing Digit, which is the first mass-producible, low-cost, high-resolution, compact tactile sensor. And Digit is a vision-based tactile sensor, so it uses the same technology as GelSight, but it has a smaller form factor, so that it can actually be mounted on an Allegro hand, for example. And the most important thing is that it was designed from scratch in order to be cheap to manufacture and easy to manufacture, so that anybody can essentially just 3D print the external mechanical parts and can order the electronics, for example, from China very easily, and assemble it in a way which is also easy to assemble. It's reliable, it's very robust. And it's USB, so it's also easy to interface. And in terms of quality, is maybe not up to the level of the original GelSight, but it still presents sort of some of the similar rich features that you would get from the sensors that TED produces at MIT, which are amazing. And most importantly, as mentioned before, this was open source. It was the manufacturer is actually very cheap. If you would be manufacturing 1,000 units, it would cost about $15 for sensor, and has several advantages compared to other commercially available sensors, which are typically more expensive and with lower resolution. And the nice news that I sort of wanted to share today is that we know of at least 15 universities that have so far replicated the sensor and that are using it in the research, which is a great news, and we are super happy to try to sort of assist this effort to essentially use Digit in research. And it's open source, so if you're interested, just go to digit.ml and you will find more information there. Now, this was last year in terms of hardware, but the second pillar, which was something that we've been working more intensively recently, is simulation. Simulation is really a fundamental tool in the toolkit of a scientist, because it allows to essentially prototype, debug, and benchmark new advances in robotics, in our case, without the need to access physical hardware. And to a large extent, if you're not a robotician, it's very difficult to work on tactile sensing, because you might not be sufficiently familiar with hardware to actually know how to use a physical sensor. So, and the problem there is that most of the traditional rigid body dynamics physics engines do not really support rich tactile sensors like the GelSight or Digit, but only support low-dimensional sensors. And as the number of sensors scales to hundreds or thousands, it becomes impractical to use these traditional sensors that are incorporated in the rigid body dynamics, because it becomes slower and slower and makes the simulation essentially slower than real time. This is our image that we did. We created almost a decade now ago on simulating the skin of the iCub using Gazebo, and at some point it was taking a couple of seconds to simulate every 20 milliseconds of real-world interaction. So it was order of magnitude slower than the real world. And this is not desirable, because you actually want to be able to have a simulator which is fast and that allow you to test things quickly and debug them quickly. So our a small contribution to this has been in December of last year, the open sourcing of a simulator which we call Tacto, which is explicitly designed to be fast. When we sat down and we were thinking, okay, what are the characteristics that we want to have in this simulator? We wanted to be able to simulate thousands of objects, and we wanted to be able to have the sensor interact with thousands of objects at hundreds of hertz, because we think that speed is important. And we sort of at the spectrum that Wenzen was mentioning before, we make a lot of trade-offs in maybe in the quality of the simulation just in order to be fast. But at the same time, we also, as I will mention in a little bit, we actually also have very realistic renderings. So the type of features that Tacto has is that it's extremely fast. It's 100 to 100 frames per second. It's general purpose in the sense that it can actually simulate different types of sensors, vision-based sensors. And from a physics point of view, it's not accurate. It's certainly not as accurate as a finite element model. But the trick that we employ here is that we essentially completely separate the simulation of the tactile sensor from the physics engine, which means that you can plug in the physics, your favorite physics engine, including rigid body dynamics physics, which is really cool, because although the simulation of the physics will not be super accurate, it's actually very fast, and it's kind of agnostic to the underlying choice of physics engine. At the same time, on the rendering side of things, the rendering of the images is extremely accurate, as I will show in a second. And because we have this assumption that underlying physics model can be also a rigid body, we essentially do a couple of tricks so that the actual deformation of the gel is modeled on the rendering side. And this enables to simulate different types of deformations of the gel and characterize this deformation. Which also means that this simulator can be calibrated from real sensors, for example, from digits, which is really cool. And finally, this simulator is open source, so anybody can contribute. Now, just to give a clear idea of how this simulator actually works from an architectural point of view, what we have here is that we have Tacto has the capability of interfacing with different physics simulators. The one for which we provide most support and an interface is PyBullet, but it can in theory be integrated with any other rigid body dynamics physics engine. And internally, Tacto makes use of a renderer, of an existing renderer, which is called PyRender, which is designed from people at UC Berkeley, and is extremely fast and can be used in conjunction with GPUs to make the computation even faster. And finally, this simulator can essentially load different sensor configurations files so that it's possible to simulate different sensors, for example, digits or OmniTac. And something that was very cool for us to see was that when simulating the OmniTac, which is the sensor at the bottom left, the simulator actually captured the fact that because of the light placement that the sensor has, the images are tending to be pinkish. This is again because of the actual simulator, because of the light placement, and this is it's actually what's happening in the real sensor, which is very interesting because then, as was already suggested before by Mattei, for example, this might actually be a first step toward being able to optimize the sensor design in simulation. For example, the placement of the lights, and being able to do this in simulation without having to physically manufacture sensors. which we believe is something that will be very, very relevant in the future. And I know that Wenzen is also very heavily working on this. I think it's an amazing direction to work. And finally, as I was mentioning, this simulator can be calibrated using real-world data and from sensors. And in here, you can see a comparison between simulated images and images captured by a real digit sensor with different intensities of forces. And you can see how qualitatively the renderings are fairly accurate, are fairly realistic. It's actually almost hard to say which one is the real one and which one is the simulation. So the next step after simulation is touch processing. And I think that this is a really, really important topic. And I would like to draw here a similarity to the past and to history. I very strongly believe that touch will be the next field of computational science. And I draw the comparison to introduction of the first telephones at the end of the 19th century, which essentially through the widespread diffusion of hardware and cheap hardware, essentially created then the corresponding computational fields of processing for audio, signal processing, and more recently, machine learning-based fields of computational science for audio. And more recently, at the end of in the 90s, the widespread diffusion of cheap digital sensors that could capture images and digital cameras essentially led to a similar creation of a field dedicated to the computational understanding and processing of images, which is now computer vision, which is an extremely successful and sort of global field of research. And I'm very strongly convinced that we are essentially at the edge in history to have cheap, reliable tactile sensors. And we believe that the introduction of this type of hardware will lead in the next decades to the creation of a computational field dedicated to processing of touch sensing informations and understanding of this information and transmission of these informations. And we are very, very focused on essentially creating this field and sort of furthering research in this area. So far, there is extremely limited literature about computational processing of touch sensing. There are a lot of papers individually that give contribution to specific applications and problems, but there is not a consistent theory. There is not a overarching, I would say, a field dedicated to this. And there are, at the same time, very important questions that need to be answered and studies. First ones, what are good features for touch? What type of sensors do we even need? What representation do we need? What computational structure do we need in order to process touch sensing? In computer vision, for example, convolutional neural network are extremely popular. What would the equivalent of a convolutional neural network look like for a tactile sensor? These are, I think, really important questions. And sort of as a way to give us more contribution toward this goal and to further the research in this field, we open source and presented at ICRA the first machine learning library explicitly dedicated to touch processing, which we call PyTouch. And the goal here is that we want to create what is the equivalent of OpenCV for vision, but for touch. And PyTouch is sort of built with the idea that it's going to be a framework which is flexible, it's modular, and it's really dedicated to furthering this field, this sort of newborn field of touch processing. And some of the important features that PyTouch has is that it's machine learning libraries, and it's based on PyTorch, which is an excellent platform, very widely used in the machine learning community. It presents very well thought and carefully studied abstractions, for example, which are hardware agnostic, that try to enable and really support rapid experimentation. And moreover, the whole platform is thought in order to standardize also the evaluations and comparisons of different models. Ideally, we would like anybody, if you have a new model that you want to try out, we would like you to be able to implement it quickly in PyTouch and directly compare it against all the other baselines that are implemented there. And at the same time, if you're not a power user, but you're just a practitioner, or you are not a machine learning expert, we want still you to be able to use PyTouch as a service by essentially just downloading our pre-trained models and use them in your applications as a building blocks. Although you might not really understand what's going on, in most cases as a user, you might not even care about that. And having pre-trained models, we believe it's crucial in order to enable a wider sort of community to be able to use Touch. Finally, PyTouch has native integration with Digit, which is our hardware, and Tacto, which is our simulator. And we are currently working on also trying to include support for non-vision-based tactile sensors. So we will actually, love to be able to support this. And again, this is fully open source, so anybody can actually contribute to this library. And here I just wanted to give very quickly an example. This is an example of 10 lines of code, which is actually downloading. It's essentially using a Digit sensor, and it's essentially downloading a pre-trained model to detect touch sensing. And then it's querying this model from data from the Digit in order to detect if there is a touch, if the sensor is being touched or not. And this is, it's super compact. It's taking care of all the boiler code templates, and it actually works. Another thing that is nice is the fact that we can actually train models which are across different sensors. And in the paper, we show that you can actually train joint models using inputs from different Digits and OmniTac and gel sites. And when this model is then evaluated on a new sensor, using this joint model actually outperform using models trained only with data from one particular sensor, which sort of hints already at the fact that there must be some feature of touchiness which is shared across different vision-based tactile sensors. And this is something that will need to be investigated more in the future. Finally, the last bit, which is we believe very important, is benchmark and datasets. And benchmarks and datasets are always a tricky thing because it's a community effort. We need to agree to a large extent to what are the tasks that we care about in benchmark. And we believe that we now had, so far, historically, it was very difficult to create benchmarks because there was a lack of standardized hardware and there was a lack of simulators. But now that we do have hardware which is more widely available and we have simulators, we believe it's important that we start thinking about what benchmarks we care about and really discuss as a community about this. And similarly about datasets, there are very few datasets in tactile sensing, and sort of to stimulate the discussion as a part of our of our simulator paper, we also created the first simulated dataset of over 1 million grasp. And then we trained different models from just using touch and using vision and touch. And we essentially started working at a different data regime, which was never explored before. The largest dataset prior to this simulated one was 2 orders of magnitude smaller. Now, almost out of time, so I will just very briefly mention a couple of applications we've been working on. One application is 3D reconstruction from vision and touch. This is a paper that was published at NeurIPS last year. And the idea here is that we want to be able to merge global informations that are captured from vision together with very high resolution, very accurate informations that are locally captured by touch. And we presented a method which is very smart in how we can essentially merge this local and global information. And also yesterday, we open source we published a new paper on Archive about learning how to play piano using touch, where the idea is that we want to be able to provide a music score to the robot and using reinforcement learning, essentially learn how to play accurately so that we generate sounds and music which actually match the scores. And here is a brief example of a very simple part, which is learn from our model. Finally, community. I just want to point out that we created a Slack workplace at touchsensing.org, and there are already 50 people, more than 50 people joining there, and we really would like people to have a place to discuss about science in touch sensing, also beyond these amazing workshops that happens only once a year. I think we should have a continuous discussion and sort of discussion really within the community. To conclude, this work has been possible thanks to the amazing number of collaborators, and I thank all of them, in particularly Mike, Sean, Harry. They were really the people that did most of the hard work that I presented today. And to conclude, we have been working on really creating this ecosystem that allow to simplify the integration of hardware and touch processing, and to ultimately enable us to perceive, understand, and interact through touch. And we are very focused on trying to grow and support the community. And our long-term goal is to make touch sensing practical and more accessible both in research and in the real world. So thank you for your time, and I'm happy to take questions.
Thanks for the presentation, Roberto. It's great to see that there's lots of efforts on the Facebook side supporting tactile sensing research. And it's very nice to have the efforts of building the community and share with the community. Okay, so we're almost running out of time, so there's only time for one question. So I saw there's one question from the chat window saying that, are there any domain randomization available for better sim-to-real transfer in tactile?
Sorry, can you repeat the question?
So are there any domain randomization available for the work on sim-to-real transfers for tactile?
The answer is yes. It's something that is not published, but we have been working on this, and it actually works. So we hope to be able to share this with the community very soon. And I think it's a really important direction, especially since the simulator is not physically very accurate. So using sim-to-real techniques might make it more robust.
Mm-hmm. So I saw Lorenzo already want to ask a question. So let's try to make this quick. One more question.
Yes, I was just wondering if you did any comparison between the response of the tactile sensor in simulation to force, and instead of just the geometrical feature.
Yes, so in the paper we also we essentially show some example with varying amount of force, and the simulator can essentially support different amount of force. Effectively, you can specify a transfer function of how you think that the elastomer will react to force, and essentially this will be taken care into the simulator. So the more force you apply, the more essentially you will see things being squashed.
Okay, thank you.
Okay,